All right, let's get started, everybody. Today's class is going to be covering loosely material from chapter 9. The next reading is it's a journal article by something Kirk, I don't remember. That's going to be on the last topic of this unit, which is correcting comparisons. Originally, I had planned on covering comparisons on Monday of next week, but after doing prep for today's class and also for this unit, there was one flex day. What we cover today is going to spill over a little bit into Monday. That'll be good too, because I think it'll be helpful to go through a couple extra examples of this kind of design. I think it's going to be relevant to a lot of you. So that's I guess I didn't share with you my specific schedule, but that's a change that I'm making from my original intention. We're not going to be covering multiple comparisons on Mondays. That will continue with today's topic. Anyway, though, if you did want to read ahead, the Kirk reading is what you're going to be asked to do next. So I'm going to ask you to start that on Monday, or maybe you can start it now if you want. One other note about the course schedule. So we're going to have our first take-home exam, I think, the week after next month. The only thing that's going to be on the take-home is stuff from this unit. So stuff about categorical variables with 3 or more levels. So that week we will be starting a new unit. So this is, I'm talking about 2 weeks from now. We'll be starting a new unit, but none of that new content is going to be covered on the take-home exam. Questions about the schedule? All right. So today we're still going to be focusing on these first 2 cases that I've laid out as like the types of cases where you might be encountering this kind of variable. Essentially what we're going to be doing both today and Monday is applying some of the concepts that we learned last semester. So about statistical control, we already saw that come up a little bit. About interactions and how that affects the interpretation of your coefficients. We'll be applying some of those concepts to this type of design. Because as we've seen all along, these concepts, they apply perfectly well to all the different extensions that we covered with the general linear model. Sometimes there's a slight change in some aspect of it, but that's going to be true now. So the same concepts as just control and interactions and all that good stuff applies perfectly well here. Today, I'm going to first go through an extension where we're looking at an additive model. So you're adding in an extra predictor variable into the model. We'll see what that does. After that, we'll extend to an interactive model. And what I'm going to do is stick with one data set, one research scenario. I'm going to be using the same data set or research scenario the entire lecture today. And that'll allow you to see, what changes when you move from the additive to the interactive model, and what stays the same. Monday we'll get into other research scenarios, but today I'm just going to be focusing on one. So we're still going with this, drinking and anxiety sort of research design. We've still got 100 people each that either drink alcohol, don't drink anything, or drink a placebo. One thing that's changed is that for this research scenario, you can measure someone's startle response independent of any sort of drinking. We can basically blast some white noise at them, and that's what you do to evoke startle. And you measure how much startle they have at baseline. And in this particular area of research, many people think that's a measure of like trait anxiety. So if you startle a lot, you might be anxious most of the time. If you don't startle very much, you might be just generally a low anxiety person. Another important note here is that, of course, we're assuming that beverage condition, whether you drink alcohol or placebo or nothing, is randomly assigned. Not just going to say arbitrarily, I don't think this is true, but I'm just going to declare that anything below 20 microvolts of startle, that's how this is usually measured, is electrodes, is not clinically relevant, but if you get a difference above 20 microvolts, that is clinically relevant. The outcome is still startle response after you drink whatever it is that you're drinking. And the hypothesis, as we've seen in these research scenarios, that specific hypothesis is often pretty important. So our hypothesis here is that alcohol will reduce anxiety. The placebo, so the expectations that you're drinking alcohol won't do anything. It'll have the same effect as if you didn't drink anything. Okay, so this is the hypothesis. What I want you to do is take maybe a minute on your own and write down what you think the two contrasts are that represent this hypothesis. Looks like people are done. Who can tell me what C1 would be, or one option for C1?
Negative 2/3 for alcohol and 1/3 for C1.
Right. Negative 2/3, 1/3, 1/3. If you prefer, this could also be -2, 1, 1. It's also perfectly fine to reverse the signs if you want. You just have to be aware if you're interpreting the coefficients at the end that you have. So that'll give you the same magnitude of coefficient, just have the sign. Perfect. How about C2?
I said 0, -1/2, and then +1/2 to make
Right.
sure that they're actually the same.
And in general, what sort of situation are we dealing with? Are we dealing with a situation where we have very specific predictions and we're capturing deviations from those predictions? Or are we dealing with a situation where predictions are spread out across multiple contrasts? variables.
More specific.
Yeah, so the hypothesis is framed very specifically. It says exactly what how expectations will compare to both alcohol and nothing. It also says how alcohol will compare to placebo and nothing. So in general, if you're in this sort of research scenario, you need to make sure that your hypothesis is specific. That's what this scenario is designed to do, is capture something, a very specific pattern, and then look at deviations from it. Any questions on that? So this is something that we've already done before. We've learned how to do this. We've even worked with this particular set of contrasts, so that should be familiar. One note about this research scenario too. So I mentioned how there's another variable, not just like which beverage someone is drinking. There's this baseline startle response. And it's important that that little bit of information that I gave you, that it was measured before the beverage manipulation, and that the beverage manipulation was randomly assigned, is pretty important. Because that might tell you how we intend to use this particular variable. So last semester we learned how sometimes you might use some extra variables that you include into a model as for causal identification. You have some sort of causal effect, you have a particular causal model, and that causal model tells you what you need to control for in order to identify your effect of interest. But there's a second thing that covariates can do. That second thing is they can just give you extra power to test the effect that you're interested in. So I've drawn like a bunch of different arrows up here. The reason I've drawn all these is that the fact that the beverage condition, what I call alcohol up there, the fact that that's randomly assigned, and the fact that baseline startle is measured for that assignment means that we know that this double-headed arrow can't be there. That's what the random assignment buys me. That should tell you then that the way that we're intending to use this extra covariate, this extra variable baseline startle, is primarily to increase statistical power. So we're primarily interested in what these three beverage conditions do, and including baseline startle as a covariate can give us extra precision. So this is stuff that we talked about last semester, but you can sort of see it in action playing out in this scenario. So the first thing I'll do is, we can see what happens when you do use baseline startle as a covariate. And specifically what I'm going to do is test an additive model. I may have used that term last semester. Additive just means I'm adding an extra variable while not allowing it to interact with anything else. So these are these data in this particular instance. These are the data that we're working with. And we know what our two contrasts are. We know what our extra variable is that's quantitative, that's baseline startle. Let's first see what happens, or follow the same procedure that we had before, where we replace these text labels with numbers, with the contrast values that we're using. So I'm color coding these because I'm going to be mixing the points up later. this is what it looks like when I replace those text labels with my C1. That contrasts, that compares alcohol to the average of placebo and nothing. And notice, of course, placebo and nothing have the same number up here. But I also want to incorporate one more variable into this model. I want to incorporate baseline startle. And the way we approached this problem last semester was, well, you can get some extra information on this graph by color coding each point according to its level of baseline startle. So if this point has a low level baseline startle, you might give it one color like red. If this point has a higher level of baseline startle, you might give that a different color like blue. And you can color them according to a gradient from low baseline startle to high baseline startle. So that's what I'm going to do. And I've taken away the color coding according to the average group because I need that color to display the information about baseline startle. But you already know how this graph relates to the first one that I showed. So this is what that looks like when you do that color coding. We've got some points that are more reddish, some points that are more bluish. And a lot of them are kind of mixed up, but you might be able to see that the points further towards the top are a tiny little bit more bluish, and the points closer to the bottom are a tiny little bit more reddish. So now that that's done, you can plot what happens at the average level of baseline startle. Turns out that that's the same, basically the same coefficient that you get if you just fit a two-parameter model of baseline startle predicting follow-up startle. Some differences based on the correlation between baseline startle and whatever's down here. But by design, I'm dealing with a situation where there's not that correlation because the average condition is random this time. You can also plot what happens at lower levels of baseline startle and higher levels of baseline startle. So I can put a prediction line for whatever level of baseline startle that you want. And what happens, of course, is that at lower levels of baseline startle, so this is the average level minus 100, you nudge the full line down, and at higher levels of baseline startle, you nudge the line a little bit further up. This is exactly the same process that we followed when I introduced these multiple predictor models. So that's that last graph that I showed you. This is how you fit this kind of model in R. So at the top, I'm still creating those two contrast variables using case one. You might have used if else to do this, or you might have used the contrasts function. Doesn't really matter, though they'll all get you to the same place. Basic idea, I'm just making variables that instantiate this code. Then when I use LM, I add in as predictors C1, C2, and baseline startle. Yeah, go ahead.
I have a question, and I just missed this. Why do you have the mean minus 100 and plus 100? Is that?
So I could have plotted -1, but the lines end up right on top of each other. So if I do -1, this red line is like right here.
But why do you have those two extra lines?
Just to show what the prediction line looks like for the relationship between C1 and startle when I set baseline to a lower value.
Okay, so you just kind of picked an arbitrary low and high value, okay.
Exactly. I could draw a line like that for any value of baseline startle that I want. And it would just, the line would get nudged up if I chose a higher value, or get nudged down if I chose a lower value. So that makes sense.
Right, so that, but it doesn't have anything to do with the interpretation output.
Well, what we're, no, where we're heading next is we're going to tie this output back to the graph. So it sort of does, but the only reason I chose the mean minus 100 is so that you can see things on the graph. Does that answer your question?
I think so. And so you said, sorry, the base startle C, it's base startle minus the mean of base startle?
Yeah, that's centered baseline startle.
Okay, okay.
Everything clear? So you know the drill. We've done this before, many times in fact. How do you think that this intercept, the 46.49, how do you think that's represented on this graph? Yeah.
That green line, right?
Yeah, so we follow this, so we follow this gray line, and it's where the gray line meets up with the purple line. Or alternatively, it's where the purple line crosses this dotted line. That's the y-axis. The intercept is always the predicted value at 0 on all of your predictors. That's the y-intercept. So one way to use that, use this in a sentence, is that the average startle response for someone who's average on baseline startle, averaged across conditions, is 46.49. So yeah, that's the intercept right there. Intercept has the same interpretation as it always has. How about this coefficient for C1? Where do you think this is represented on the graph?
Slope as you move from alcohol to the conditions.
Yeah, great. So I plotted C1 on the x-axis. The coefficient is the predicted change in our outcome. So follow-up startle response for 1 unit increase on whatever the predictor is. And in this case, the predictor is C1. So that's 33.19 is the slope of any of these lines. In fact, it's the slope of all these lines. What's another way to think about what that C1 represents?
C1 represents the difference between alcohol startle response and the combined placebo method.
Absolutely. It's the mean difference comparing people who drink alcohol to the average of the people who drink placebo. What about this C2? Actually, I'll just give this one away. You can't really find C2 on this particular graph because I took away that color coding, right? I took away the color coding that tells you who in this group is placebo or not. I'll get back to C2 in just a moment. But you can't directly pick out C2 on this particular graph. I'd have to create a new graph or change this graph. One thing I will note though, tying back to some of the information I gave you at the start of the lecture, if I set this threshold for what kind of startle response is clinically relevant, I just want to note here that C2 is well beyond that clinical threshold. So this is probably a difference that I ought to care about. And maybe it would even threaten the overall hypothesis that I gave you at the beginning, that alcohol or that placebo will have exactly the same effect as if you did nothing at all. So this is the kind of finding that might cause you to say that your hypothesis was falsified, or at least threatened. If this C2 was below 20, below that threshold of clinical relevance, that's when you might do an equivalence test to say that it's significantly below the threshold for what you consider an important effect. And you use LHT to do that. Okay. What about this new coefficient, the coefficient for baseline startle? Where is that represented on this graph? So I'll tell you something that we know it's not. It can't be the slope of any of these three lines, because that was C1. So what would it be instead?
It's a proportion of the distance between one of the baseline lines that you've augmented, accumulated, in comparison to the mean one.
Perfect. To restate what you just said, it's the vertical distance, or rather 1/100th of the vertical distance between any two of these lines at any point. So the amount by which you have to go up, that's that coefficient times 100. Decided. In order to allow you to see this, I subtracted by 100. So does that make sense?
So, how is that useful, or I mean, what do you do with that information?
Well, I want you to be able to see visually how these concepts play out. You know, if you learn a concept in a bunch of different ways, it builds understanding. We're also going to see that when we move to interactive models, some of these things change. So I guess if you see a graph and you multiple lines are plotted, you know that that represents something important about the model. That can lead to new insights. If you graph things on your own, that can also lead to new insights. Technically, you could get all this information from the model output. Like I said, though, I mean, I find it instructive to look at something from a bunch of different perspectives.
Right. So, but in this case, aren't we predicting outcome startle based upon baseline startle?
Mm-hmm.
And then, so how are we using this to say that baseline startle did or did not predict outcome startles?
If you want the significance test, you have to look at this model output. I suppose a larger vertical distance between any two of these lines would be more likely to be significantly different from zero.
Was it though in this case?
Yeah, so if you look at the output at the t and p value, that's significantly different from zero. Yeah.
I have a question. So I guess this is what I'm struggling. So in this graph, all the points that are plotted, is the baseline startle centered in the graph?
So it doesn't matter. So the lowest points, the points that represent people who have the lowest levels of baseline startle will always have the red points.
Yeah, I cannot see the color difference at all. I think that's what I'm also having trouble with. It all looks like the same.
Okay.
color From here. So I'll just look pink and purple.
Yeah, it might be a little bit easier to see when you have the slides in front of you than it is from a distance. In general, there are more red points down here, but it's true that they're all mixed up a little bit together. We'll see another visualization of this where it might be clearer what this relationship looks like. It might be a little bit hard to see here. But to the extent that more of the red points are down here, you would get larger vertical distance between these lines. So those two things will match up. Is that helpful? Or,
Can you repeat that? Sorry, one more time.
if most of the red points were in this lower region of the graph on both sides, that would pull this red line down more. But if all the points were completely mixed up and it was just random, these lines would be completely on top of each other. So those two things will link up together. If most of the points, the red points are down here, it sort of exerts some weight on that line, it pulls it down. Is that helpful?
Yeah, I just don't know how to find that on the graph.
Best place to look is the vertical distance between these lines. It might be hard to see, but you can sort of see that there's more shading up to purple as you move up on these points. And most of the points up here are blue.
So it's the difference between the vertical one. But that looks like it's a lot more than 0.6.
Yeah, so this is going to be 60. It's
Oh, because it's the difference of optics.
Yeah.
Okay.
Does that help?
Mm-hmm. And it's just weird to think about looking.
It's just because of how these variables are scaled. Startle response usually goes from minus 100 to 300.
Mm-hmm.
If you want, you can divide everything by 100, and it might make a little bit more sense. Does that help?
Yeah.
Can I attempt an interpretation?
Sure.
So is this saying that by adding baseline startle into your model to predict outcome startle, it's increasing your startle by 0.6 points?
Yeah, you can think of this as like pre-test and follow-up. So before drinking, every unit increase in startle that you have before drinking is associated with a 0.6 unit increase in startle response after drinking.
Or after whatever condition.
Yeah. Yeah, so you're
Average
absolutely right.
across conditions.
Yes, average across conditions, that's also important. Is that a little bit clear? So I hope some of this is familiar because this is reviewing concepts that we talked about last semester. And something that comes out of all this is that the same principles apply here as they did when we originally covered this. Okay, so I'm going to try another visualization because on the last graph, I mentioned how we're missing C2. That wasn't immediately apparent. So I'm going to give you a visualization that more highlights C2 and allows you to see what's going on. So just as I did with C1, with the focal contrast, I just replaced the text labels with the numbers that we designed them. So -0.5, 0, and +0.5. I'm taking away the color coding by group now. And I'm going to replace this with the color coding according to baseline startle. You can see at the top, those top couple points are blue. It might be a little bit hard to see, so sorry about that. Maybe try slightly more contrasting colors. But anyway, now that I've done that, you can draw prediction lines at different levels of startle response. So at the mean of baseline startle response, minus 100, plus 100, and I could have drawn any number of other prediction lines. You know, I can draw one for any particular value of baseline startle response that I want. So here's our model output. And I'm going to skip ahead to C2 for a second. So where do you think C2 is represented on this graph? What about the purple one? It's the slope of the purple line. All I've done is I've switched what's on the x-axis. Now that C2 is on the x-axis, this slope represents the vertical distance that I have to travel, the amount by which I have to change my predictions for follow-up startle response for 1 unit increase in C2. And so what's one way of understanding C2 in this example?
Difference in means between placebo and nothing.
The difference in means between placebo and nothing, which is 51.98. So going back a little bit, just like with my previous graph, the intercept is where this purple line crosses the vertical dotted line. And in fact, it's exactly the same y-intercept that we had on the first graph. It's the same data, same model. C1, now that I've taken it away, you can't directly see it on this particular graph because I've color-coded these points according to baseline startle. And baseline startle is still proportionate to the vertical distance that you have to travel to get from, say, this line to this line. So the graph looks very similar. I'm just highlighting something slightly different about the data. So there's one extra way that I could visualize these data to kind of understand what's happening in our model. And that is to highlight startle response. So maybe this will help you understand that relationship. So what I've done for this graph is I've just plotted baseline startle on the x-axis. I'm going to mean center it because to better match up what the statistical model is that we did. So I've just shifted the axis. I hope you can see that. Same data, just shifting the axis. And then I can color code these points by whether they belong to someone who was given alcohol, placebo, or nothing. So I'm using the same color coding that I showed you in the very first graph where I introduced all of this. But I've just plotted baseline startle on the x-axis. And I can plot prediction lines for each of those three groups. So this green line is the prediction line for people who were given alcohol. The red line is the prediction line for people who were given placebo. The black line is the prediction line for people who were given nothing.
And the gray line is the average startle response?
Yes. And the vertical dotted line is just the yeah, this is the y-axis. And the mean baseline startle in this point because we mean centered. Okay, so let's try to tie these quantities to this new graph. How do you think that the intercept is represented on this particular graph?
the grade of the dotted line, right?
Yeah, absolutely. So one interesting thing about this graph is that before we saw how my prediction lines I actually like matched up somehow with the that y-intercept, but here they don't. So that's interesting. That's slightly different. Why do you think that is? Why isn't the intercept where one of these three lines crosses the axis?
The intercept is when everything equals 0.
Yeah, and my contrasts are centered. I've set it up, I've constructed it so that the intercept will be the green beam. The things that have non-zero numbers, well, so when I'm thinking about what 0 represents kind of the average of the three groups. But I plotted prediction lines for the three groups. So this is a slight difference from the graphs that we saw and many of the times that we've done this exercise in the past. The intercept is not where one of these three lines crosses the y-intercept. It's somewhere in between them. How about C1? Where do you think C1 might be represented on this graph?
It's probably pretty hard to see because placebo and nothing aren't like averaged together in this graph. So it's pretty hard to see.
Yeah, absolutely. So what I'm going to do is draw one extra line to sort of help you all see where this quantity is represented. I'm just drawing a prediction line at the average of placebo versus nothing, those two groups that were assigned the same number. That line literally ends up being halfway between the nothing line and the placebo line. It's the average of those two groups. So now that I've drawn that line, can anybody point out where this coefficient might be represented? Yeah.
Is it the difference between the dotted line and the alpha line for like the vertical distance?
Absolutely. So choose any point on this graph. It's the vertical distance between those two lines. This is another way of understanding what you're doing when you assign groups the same number using contrasts. You're treating them as equivalent. You're taking the average. Literally on this graph, you end up drawing a prediction line at the average of those two other groups. What about C2? Where do you think C2 might be represented on this graph?
Is it the vertical distance between the nothing line and the placebo line?
Yeah, absolutely. So you find the nothing line and the placebo line, that's these two groups, the two groups that were averaged together when we were looking at C1. And it's that vertical distance. Anywhere along the baseline start. How about the coefficient for baseline start? Where do you think that might be represented? Yeah, it's the slope of any of those three lines. So that's the thing that's highlighted on this graph. in order for you to see it, I drew it all the way out to 100, so it's 100th of that vertical distance. This should say vertical distance rather than slope. But anyway, it's the vertical distance that you have to travel, the amount by which you have to increase your predicted follow-up startle response for 1 unit increase in baseline startle response.
Can you repeat that interpretation?
It's the amount by which you have to change your predicted follow-up startle response for 1 unit increase in baseline startle response. Or in terms of what's happening in the graph, it's the vertical distance that you have to travel to match the prediction line if you travel 1 unit in baseline startle response. Yeah.
Sorry, I just keep getting confused about this whole 100 thing. Why is it 100?
Yeah, so this is a little bit misleading here. Really, it's the same slope. I traveled out from 0 to 100 in order to make it more visually apparent what's happening. So it is true that that 0.6 is 100th of this vertical distance. But of course, the slope is the same regardless of where you are on the line.
Right. Okay. So it would be this slope.
Yeah, it's the slope.
Okay.
I'll fix it. So that's a bunch of different ways of understanding what's happening in this additive model. We've worked with all of these different concepts in the past. So we're just applying those concepts to a new example. And that's generally true. So if you add extra variables to a model where you already have a set of contrasts, the same concepts apply. There's really basically nothing new here. Let's see what happens when we're looking at an interactive model. So the question that you might be asking, the conceptual question might be, does beverage condition, just what you drink, does the effect of that on anxiety differ based on your state anxiety? So is the effect of the beverage manipulation different depending on your state anxiety or your baseline startle response? One thing that is a little bit different from other interactive models that we've looked at is that, so we want baseline startle response to interact with beverage condition. But beverage condition is not represented by just one thing in the model. It's represented by 2 things. Because we needed to create 2 mechanical variables in order to fully represent beverage condition. So that's different. We haven't worked yet with variables that are represented by multiple things. The solution is actually very straightforward. So we have 2 variables representing, or 2 mechanical variables rather, representing this one big 3-level categorical variable. So when we allow baseline startle to interact with beverage condition, we just create 2 new interaction terms. We literally multiply baseline startle by C1 and create a mechanical variable representing that interaction term. And then you do that again. You multiply baseline startle by C2 and create an interaction term for C2 by baseline startle. So you've got 2 variables that represent this like 3-level categorical variable. Well, if you want that 3-level categorical variable to interact with something else, you need to create 2 interaction terms. That's all you do. So literally in R, what you can do is just multiply C1 by center and baseline startle, and C2 by baseline center and startle, and create those two new variables, and then add those to the model. So that's one way you can do this. You literally create mechanical variables in your data frame, and then add them to the model just like you would with anything else. R gives you a couple ways of doing this, including some shortcuts that are often handy. So I'll show you some other ways of doing this. That's more for reference. And there's one syntax that I usually use because it's quick. So another way of doing this is using the colon. Colon just says add the product of this and this, whatever is on the two sides of the colon. Another way of doing it is the star. The star is what I've usually used in class. So you could say, add C1 and C2 and that interaction, and then C2 and star and that interaction. You can also use parentheses. Parentheses basically, it's distributive basically. That's saying, hey, I want everything in these parentheses to interact with baseline star. So it just saves a little bit of typing. Everybody clear on how this works? I suppose there's one other option if you're working with those factor variables, those like that special variable type that R has to deal with categorical variables. If you have a factor variable called condition, you can say I have a condition, however that's coded in your contrast. Interact with start, so you can put a star with. These are all equivalent. You've probably seen in drill, sometimes it's a little bit more convenient to work with factors. But in R, basically the same rules apply with these categorical variables as apply with other kinds of variables that you have. So this is that first visualization that we looked at, where we have C1 plotted on the x-axis, and I've drawn different prediction lines at different levels of start. So what I'm going to do next is show you what changes when you allow beverage condition, C1 and C2, to interact with baseline start. So what changes here is that whereas before all the lines had to be parallel, now I've allowed them to not be parallel. That's you can think of that as the constraint that we're relaxing in our model. Before we assumed parallel lines, now we're allowing the lines to not be parallel. And remember, this is exactly how interactions worked last semester too with other kinds of variables. We saw that one way of thinking about interactions is that you're allowing lines, the slope of one line to vary across levels of another. So we're allowing the slope of the prediction line for C1 to vary across levels of baseline start. Yeah.
I'll try to interpret this. So are you saying here that the change in style between the alcohol condition and the CO methane condition differs depending on whether they have higher or low baseline style?
That's perfect. That's very good. So yeah, that's Something that is different now that we're working with contrast variables. We saw how you can think about contrast variables as various types of difference scores, right? This happens to be a difference score between what's happening in the alcohol condition and what's happening in the average of the placebo and the nothing condition. So one way of thinking about this is that difference between the alcohol and the average of placebo and nothing changes based on someone's baseline startle response. So let's see if we can do the same exercise where we're sort of tying the quantities that you might get from R to what you see in the graph. So I'm showing you this interactive model. That's just the model that I fit a couple slides ago. I'm just going to say up front, a lot of these interpretations are going to be the same or similar. But we do have two extra coefficients. I want to focus on those extra two coefficients because they're the things that basically change the interpretation of this model. So based on what we've just discussed, how do you think this coefficient, the coefficient for the interaction between C1 and baseline startle, is represented in this graph?
C1 and the difference between the low and high baselines for the alcohol conditioning compared to the average of the other two conditions.
Yeah, it's how that changes based on baseline starting. But if we think about the graph specifically, so I showed you the thing that changed when we went from the non-interactive model to the interactive model. Suddenly, we're allowing the slopes of these lines to be different. So based on that information, how do you think that coefficient is represented on this graph? Yeah.
What would be the difference in slopes between lines?
Yep. Choose two of these lines, and it's the difference in slopes. Technically, this is 1/100th of the difference in slopes. But it's proportionate to that difference in slopes.
And since it's an interaction, the difference in slope stays the same.
You got it. Yeah. You got it. So every time I move up a unit in baseline startle, that the slope for C1 changes exactly by 0.46. It decreases by 0.46.
Having a hard time wrapping my brain around this one.
So every time I increase in baseline startle, I'm probably going to be moving up here. If I drew another prediction line for baseline startle, it would have a slightly more negative slope. In fact, it would be more negative by exactly 0.46.
So it starts to go like that.
And that's what you're seeing as we move from the red line to the purple line. The purple line is a little bit flatter. So we move from the purple line to the blue line, it's flatter still. This is, again, the same principle that we discovered when we were talking about interactive models last semester. Just applied to a different scenario. And specifically, it's a scenario where we've sort of set things up such that C1 represents a difference, a mean difference in conditions that we might have to care about. So what this graph means is that mean difference, that predicted mean difference, is going to vary depending on someone's baseline startle, depending on their level of anxiety. Something I should mention here, I don't have a slide for it specifically, but we discovered when I showed this graph before, I mentioned how you can't exactly see C2 on it. It's kind of hidden based on the color coding and how I've drawn this graph. So to see what's happening with C2, I'm going to switch the graph again. I'm going to move to that second graph where I plotted C2 on the x-axis instead of C1. So this is the graph that I showed you in the additive model. And again, each of these lines is parallel. They have the same slope. So you might have an intuition based on the previous couple slides of what's going to change when I plot the interactive model. Specifically, I allow those slopes to be different. Same principle, just applied to C2 instead of C1. So here's our output again. Here's what R tells us. I'm just going to tell you ahead of time, you can't necessarily see C1 on this graph for the same reason that we couldn't see C2 on the previous graph. Just the axes are a little bit wrong. The information is hidden. But can someone tell me where they think the C2 by baseline startle response interaction might be represented on this particular graph? Yeah. So it's 1/100th of the slope difference, just because I've gone out by 100. The general idea again is that I have to change the slope by that amount if I increase in baseline startle response. Can someone think about what the values of the contrast are and try to give a verbal interpretation for what that interaction actually means? When we were looking at C1, we found that interaction means it's the amount by which I have to change the predicted difference between alcohol and the average of placebo and nothing if I increase the unit on baseline startle response. So that was the C1 by startle interaction. What about the C2 by startle interaction?
Slope of the nothing curve is 0.21 startle units greater than slope of the placebo curve.
So that would be if you're just thinking about C2 on its own. But this is an interaction. So it's not just a mean difference. We're doing something to the mean difference. So what are we doing to the mean difference? Yeah.
The difference between the placebo and nothing groups baseline. The nothing group has a baseline.
You start out correct. So something happens to the difference between placebo and nothing. What happens and when does it happen?
The difference between placebo and nothing, startle response increases by 0.12 for 1 unit change in baseline startle.
Yeah. So as you increase the unit in baseline startle, in anxiety, you can think of it as, you have to modify the predicted difference between placebo and nothing by 0.21 units. It gets 0.21 units more positive. And this is, again, something that you can kind of see if you look at this graph, because notice how this line is a little bit flat, this line becomes more steeply positive, and this line becomes more steeply positive still. And that increase in the slope of the lines is the same every time we go up 100 units or 1 unit in baseline start.
So going even further than the more interpretation, are you saying that for those who have relatively low baseline startle, the change in outcome startle between the placebo and nothing groups is less pronounced than it would be for people with a higher baseline startle?
That's really good. So this might tell you something about why our prediction was falsified. So we found that the placebo group kind of reduced in anxiety. It could be that if you're really anxious, you have high baseline startle, placebo actually does something. So that maybe expectations are actually powerful for people who have a high trait positive anxiety. This is a tool that you can use to try to explore what happens if things go wrong in your studies, and they go wrong all the time. Yeah.
Would another way to say this be the difference between placebo and nothing anxiety? It grows 0.21 for every 1 unit increase in baseline startle.
Absolutely. Okay, this one's going to be a little bit trickier. This is that weird graph where I plotted baseline startle on the x-axis, and I've drawn separate lines for each of nothing, placebo, and alcohol. So this is what the graph looks like to start with. And I'll just show you what it looks like when we allow for that interaction between baseline startle and average condition. This one's it doesn't look as clean as the other graphs that I've shown you, right? In the other graphs that I've shown you, you can sort of see the amount by which the slope changes if you increase on baseline startle. It's just that difference in slopes. Here, it's a little bit different. You can still pick out the same quantities, but it is a little bit different. So let's dig into that a little bit. So remember, C1 is comparing alcohol to the average of placebo and nothing. So based on that information, where do you think you might, or how do you think the interaction between C1 and baseline startle might be represented on this graph?
Slope of the alcohol line, subtract from the slope of the average of the other two.
Yeah, the right intuition. So there's an extra piece of information that I can draw on this graph. Let me draw it for you. So remember, when we worked with this graph in the past, for that C1, I had to draw an extra dotted line that represents the average of placebo and nothing. So I'm going to draw that dotted line again. So notice, I've just drawn a line that's exactly in between placebo and nothing. It's just tracing out that the average of those two. So let me ask you again, now that I've drawn that dotted line, and that interaction term, or that coefficient for the interaction, has something to do with that dotted line. What do you think it has to do with that dotted line?
Difference between the slope of that line and the slope of the alcohol line.
Absolutely. So it's how the slope of the alcohol changes if I move to the average of placebo and nothing. Notice how we're sort of applying that principle of comparing alcohol to the average of placebo and nothing to something new. Before we were looking at mean differences, now we're looking at differences in slopes. Okay. What about this C2 by baseline interaction? How do you think that might be represented on this graph?
Is it the differences in slopes between the nothing line and the placebo line?
Absolutely. So C2 is comparing nothing to placebo. The interaction between C2 and baseline startle is going to be how the slope of baseline startle changes as you go from placebo to nothing. So big picture idea here. One way to think about what happens if you allow contrasts to interact with other stuff is that you allow, you're seeing how the slopes for that other stuff, say baseline startle, is different for specific comparisons between conditions that you care about. Another way of thinking about it is that you're seeing how that predicted mean difference varies across levels of, say, baseline startle. So if you care about the specific manipulation in the study that you just ran, this is a way to test whether the effects of that manipulation are constant based on something, some sort of characteristic of the person or whatever. You're seeing whether that comparison is constant across levels of something. So I recognize that some of these concepts can be a little bit hard to grasp. Just as when we went through the interactions unit, it takes some repetition and practice to understand how everything plays out. And I just went through one example today. I still haven't talked about, say, dummy codes or what happens if you look at categorical variables that have, say, 4 elements. So that's what we're going to talk about on Monday. What you'll see is that even though the interpretation becomes more complicated, or at least harder to think about, the same principles apply. You're still looking at how a particular comparison, a contrast, varies across levels of another variable, or you're seeing how the slope of one particular variable is different based on their specific contrast. So that principle is the same. So just to summarize what we talked about today, if you want to, make your models more complicated by, say, adding extra predictors or adding interactions, the same principles apply when you're working with contrast as when you're working with any other sort of variable. What's different, or at least different in how you might think about it, is that when you allow, say, a contrast to interact with something else, you're seeing how that contrast, how that specific comparison varies across levels of another variable. Another thing that's different is that because you have to have extra mechanical variables to fully represent any specific categorical variable. So for a 3-level categorical variable, you have to have 2 mechanical variables. So because of that, when you add interactions with these sets of contrasts, you have to add multiple product terms. Another thing that we saw is that, and this is just generally true when your models get more complicated, there are certain visual displays that highlight certain quantities that you might care about. And sometimes you might have to change the display in order to actually figure out how do these coefficients map onto the things that I'm actually seeing. And in particular, that last display that I showed you with multiple prediction lines, one for each level, so alcohol, placebo, nothing. That one's very common. That's one that you'll see in journal articles. Just know that you might have to think about that missing average line in order to figure out exactly how that display relates to the results that are presented in the paper. All right. Thank you very much. I'll see you all on Monday.